Hello, everybody. Happy Tuesday. It's not Happy Garbage Day, though. Not at my house, because the President's Day, the garbage is off by one day in my whole neighborhood, so tomorrow I'm going to be really confused and think that I have to show up to teach. But it will just be Wednesday Garbage Day instead. So we have some stuff to talk about. I just updated grades this morning. Most folks got the formative assessment number 2 done, so you get your 2 points. Thank you very much for that. So I have the questions open for us to discuss as a group. A few areas of confusion, but for the most part it feels like people are getting the hang of this stuff. So question number 1 to start with. If I were to take a general linear model, say regression or ANOVA or ANCOVA, and I try to use it to predict a binary outcome, what are the problems with that strategy? Most of you focused on one or the other. So what did you write down? I think I can think of it as 2 main problems. If I were to use a regression or an ANOVA to predict a binary outcome, those models are designed for continuous outcomes, right? If I decided to predict a binary one, what would happen? Will it run? Yes, it will. Absolutely it will. Will the numbers come back meaning anything? Maybe not. Okay, what's the problems? Yes. Yes, the predicted outcomes from such a model do not understand that probability stops at 0 and 1. So the predicted outcomes could go well past 0 and well past 1, which would mean that all of the inferences we would make about how a predictor relates to an outcome are probably suspicious because it's not relating in the right way. It's relating in an implausible way. This will be a greater problem to the extent that the distribution of your zeros and ones is skewed. So if you have like 50-50 in terms of the mean of that variable, you might not have a boundary problem, but the further over the mean gets, the more likely you are to hit the boundary. So that's one issue, is that it could predict probabilities above 1 or below 0. What is the other? Yeah, the residuals. So the general linear models say that the residuals are supposed to be normally distributed, have constant variance. It's not so much the normal part is the problem, it's the constant variance. There is no way that variance can be constant around a binary outcome because it varies as a function of the mean. You have the most chance to be wrong in your predicted probability for middle probabilities. You have less of a chance as you move out in terms of the variability around that point. So it's the non-constant variance. And that shows up then in standard errors that we can't necessarily believe. So the point estimate in terms of like the slopes and the relationships, that's where going out of bounds is a problem, but the standard errors for those slopes are a problem if we have the wrong distribution. So then what do we do instead? We say, okay, the residuals aren't normal anymore, they're Bernoulli. The Bernoulli distribution doesn't have a variance associated with it because it doesn't need one. The variance is the mean times 1 minus the mean, the end. What about the third assumption, by the way, of independence? So that's the other piece of the puzzle with general linear models. The residuals are supposed to be normal with constant variance and independent of each other. Has that changed or not? Yes, so the residual variance is dependent on the mean. What about the residuals of different people? They are supposed to be unrelated to each other. Has that changed?
No.
It has not changed. So the generalized linear models that we're walking into are still designed for independent people, independent observations. So a cross-sectional sample as opposed to longitudinal, or like students who are all from the same classroom or all from the same school as opposed to from multiple classrooms or multiple schools. You need a different model if you're in that type of sampling design. But the good news is that all of this would hold in those cases too. You just would have to add more stuff to the model to make it work for dependent observations instead. So yeah, going out of bounds is one problem. Wrong residual distribution is the other. Putting those together. questions or comments on number 1? The number 2, related to number 1, what is the purpose of a link function? Examples that we've seen so far being logit, log, probit is another one. What are they for?
The link function transforms so that we can have the unbounded outcome.
Yeah, the link function is a transformation. Now, does it transform the data or something else? Because what you said is correct. I'm just clarifying the language. The predicted outcome. It does not transform the data. So a logit is not a transformation that like you can do to a 0, 1 variable. It's actually undefined at 0, 1, 1. The logit is a transformation of the mean to be predicted for your outcome. So for a binary outcome, the mean to be predicted is the probability of a 1. The link function transforms that probability into something that is continuous and unbounded so that we can throw a linear model at it and have it not go out of bounds. But when you back translate, that's my preferred phrase, the technical term is inverse link. A few of you said, I think, reverse link. I like that one too. A couple different people said reverse link, I think. And I was like, yeah, that makes sense, actually. Because you're going backwards from logits into probability. Yeah, the term is inverse link, but I say back translate, reverse link I would also accept. Predicted logits will never go out of bounds when they're converted into predicted probabilities. That's the key. So link functions transform the mean to be predicted into something that is continuous and unbounded so that a linear model will work just fine. So the logit then is solving the problem that predicted probabilities shouldn't go outside 1 or 0. That's what logits are for. That's what probits are for. How would I need to know that I need to consider using a link function in the first place?
Basically, like, if you don't have a continuous variable,
Yeah, if I don't
probably you're going to need a link function.
If I don't have a continuous outcome, yep. So a few of you said if it's not normally distributed. That's not the normal part that's the problem. It's the idea of a boundary. Any kind of outcome that has a boundary of what it could possibly be, we need a link function to prevent the predicted outcomes from going outside that boundary. So probability has a boundary on 2 sides. Counts have a boundary only on the lower side because you can't have a negative count. But counts can go on forever and ever on the positive side. The same thing will be true if we predict, say, percent correct, right? The best you can do for percent correct is 100. Predicted percent correct shouldn't go above 100. We're going to revisit logits to solve that problem in a couple weeks. Same exact concern, though. So link functions are to prevent predicted outcomes from going out of bounds, broadly construed. Which boundaries you have dictates what kind of link function you would need. So, questions or comments on that? All right, to try to predict an outcome that's binary, how do logits, odds, and probabilities relate to each other? So several of you gave me formulas, several of you gave me rules. I like either one. So what is a logit? Well, say it with me. Hang on. I got to get my conductor stick out for this one. Okay. I have props. Ready? It's the log of the odds of the probability of a 1. Okay, say it with me. Log of the odds of the probability of a 1. Yes, thank you. Well done, everybody. I highly recommend one of these. I got this when I was my first year as an assistant professor, and I was like still being mistaken for an undergraduate half the time in the hallways. Now clearly that is not a problem anymore, but this makes you feel very professorial if you have a stick to gesture with or poke people who fall asleep. It can be used for that too. So, highly recommend. But I make it my conductor stick. So yes, logits, the log of the odds of the probability of a 1. So if we start with probability of a 1 divided by the probability of a 0, what's that? Probability of a 1 divided by probability of a 0, what's that called? The odds. Then if we take the natural log of the odds, that gets us to logit. So we can start from the interior and move out, or the outerior, is that a word? Exterior and move in. Are odds and odds ratios synonyms? They are not. That's confusing because if you look at odds, you're like, well, this looks like a ratio to me. There's something on the top and there's something on the bottom. No, that is not the same thing. An odds ratio is a ratio of two sets of odds. So it's like the probability of a 1 divided by the probability of a 0 for some case, and then the bottom is the same thing for a different case. So like given x equals 1 or given x equals 0. So odds ratios are not the same thing as odds. What is the neutral point on each of these three scales? Like if I have a probability of 0.5, meaning I'm just as likely to do it as not do it, whatever we're talking about predicting, what does that correspond to in odds? 1. What does that correspond to in logits? 0. How about probits?
0.5.
Also 0. Yeah. So probit and logit are both symmetric link functions where 0 means 50-50 probability. If I have a slope in logits that's positive, then I can say the logit goes up as x goes up, the odds go up as x goes up, the probability goes up as x goes up. But in terms of the units, I can only talk about the change in logits as a function of the slope. Several of you told me the rules about what you can translate and what you can't. So if I have a linear model that gives me a predicted outcome in logits, can I take that down into odds if I want to?
Yeah.
Yes. Can I take that down into probability? Yes, and you probably should to make it understandable. Now, if I have a slope in logits, like the change in the logit for a 1-unit change in x, can I take that down into odds? Yeah, it's called an odds ratio at that point because it's a slope, change in y per change in x. Can I take that odds ratio and turn it down into probability? No, I cannot. That's the step that you can't do. A few of you noted how much I hate odds. You're not wrong, but I wanted to expand on why I hate odds. But first, there's a question. Jacinta, go ahead.
I was just wondering, as we were talking, basically, if you're doing an analysis and the logit is significantly different, does that automatically mean the odds is significantly different and the probability is significantly different?
Yes. So the p-value, so the logit slope gets a standard error. Estimate over standard error gives you a z. That z corresponds to a significant probability, less than 0.05, whatever alpha you want to use. Then that logit slope is significant. So is the odds ratio. It's a 1-to-1 correspondence. I can't talk about that in terms of change in probability because it's not one number. A change in the logit corresponds to increasingly smaller changes in probability the closer you get to the boundaries. That's that S-shaped bendy function. So here's my problem with odds ratios. Okay, the world uses them, so you have to, so we have to be able to report them, but here's why I don't like them. So let's say that I have a logit slope. Let's say, make this clear. So logit slope, odds ratio, okay? So I have this in a PowerPoint. Let me show you how I got it. If I have a slope of 1, that means for every 1-unit change in x, the logit of my outcome goes up by 1. Higher x, higher y. Cool. Odds ratio, e to the that thing. Odds ratio of 2.7. So every 1-unit change in x, my odds are higher. They multiply by 2.7. What if I have a logit slope of 2? Stronger effect, right, in theory, assuming these metrics are comparable. That's an odds ratio of 7. Let me get rid of some of the decimals here to make it a little easier. Now 7 looks a lot bigger than 2, right? What if I have an odds ratio, a logit slope, of -1? or minus 2? Nope, hang on, there we go. Now, can we agree that these numbers are equally big, just in a different direction? A negative slope means as x goes up, y goes down.
I found this on the web.
No, thank you, Siri. She's like, let me help you understand odds ratios. So here's then what I end up with. I have an odds ratio of 0.37 versus 0.14. Now those numbers look a lot closer together than 2 versus 7. This asymmetry is my problem. In terms of effect size, a positive slope has from 1 to positive infinity to be an odds ratio. A negative slope is shoved in between 0 and 1, all of them. So I feel like in terms of conveying sizes of things, this asymmetry is unhelpful. Negative slopes all get shoved into numbers that look really much the same, whereas positive slopes can spread themselves out. So this is my problem with odds ratios, that and the multiplication aspect. But yes, absolutely you should provide them. I've answered at least one homework question so far about the package that I used in the example 2A is a DESC tools. At least one person's R wouldn't install it. If that happens to you, you can always just do this, e to the coefficient, and that's your odds ratio. And you don't need to compute a standard error or a p-value because you can use the one from the logit. Comment from the Zoomers, technically there is an infinite amount of numbers between 0 and 1. Also true, but it just looks like it's a lot smaller. That's my problem. Maybe it's just my problem. Maybe the rest of the world is like, yeah, whatever, this is not a problem for us. Siri doesn't even think it's a problem. But this is my problem with it. Yes, so what is an odds ratio of 1 then is corresponding to the neutral point. So when you're looking at your homework and deciding whether or not a slope is a positive or negative relationship, make sure you know if you're looking at the logit or the odds ratio. Because odds ratios will never be negative. An odds ratio less than 1 corresponds to a negative slope. That's an easy mistake to make. All right. So can I keep going then? Can I add another column over here for probability? Oh, no, because these are slopes. No. So if I want to talk about probabilities, I have to compute a prediction from the slope. I can use the slope to get a predicted logit. I can take that predicted logit and put it into probability. You cannot turn the slopes into probabilities so directly. Okay. Other questions or thoughts on that? Then last one, reviewer 3 thinks that you should fit a probit regression model instead of a logit regression model. What do we have to say? Thank you for the suggestion. That's number 1. Now, are we going to agree or disagree with this point? You're going to disagree? What are you going to tell reviewer 3?
Well, they are going to be the same thing, but for easy interpretation, you prefer logistic regression so that you can go across all those metrics.
Okay, say that louder, please.
I feel I would disagree with the reviewer. Like they are the same in terms of the model fit and everything, but I prefer logistics for easy interpretation and ability to move to all other effect size metrics like the from logit to odds ratio and probabilities if I need easily than in the product.
Okay, so the argument then is once you convert the difference in scale between the probit scale and the logit scale, the predicted probabilities they provide are pretty much the same. So you're unlikely to come to a different conclusion about any of the things that you're writing your paper about. Plus, there's a downside. Probit, or ogive as it's called in IRT world, does not have odds ratios because it's not made from odds. So you lose your ability to provide that ready-made effect size that other people find useful. And how do you get a predicted probability out of a probit? Integration. This is where we talked about last week the idea of going to the back of the intro stat textbook and looking at the Z to P table. They're doing integration for you, basically. That's what that is. So logit is easier to work with both practically and I think in terms of analysis too. Probit came first, but it's harder. There was some folks mentioned about the errors being normal versus the errors being logistic, and so I wanted to go back to that idea right here. This is this slide here, this slide over here, this one. The idea of a distribution being normal versus logistic does not apply to the binary outcome. This is a motivating idea based on the concept of a continuous underlying variable that we do not have. It is pretend. The continuous underlying variable, if we say that it is shaped like a logistic distribution, which is the flatter one, that has a variance of 3.29. If we say the pretend continuous underlying variable is shaped like a normal, then it has a variance of 1. This is just used as a motivator for plugging in these values into residual variance to get R-square type formulas. But we can't know if either of these is correct because we do not have that information. We have a column of zeros and ones and that's it. So there's no way to say that one is more right than the other. It's not an empirical question. You can use AIC and BIC to decide between link functions. In this case, that would not be as useful. But what if reviewer 3 thought that you should use an asymmetric link function, like log-log or complementary log-log? Then they might have a point. This could give different answers. So these two, here are the link functions that I'm talking about. These are designed for outcomes in which either 1 or 0 is much more frequent. And they're designed to basically take the prediction and kind of shut it off to the end that you don't have a lot of data. These correspond to the idea that the underlying pretend distribution is a skewed one rather than a symmetric one. That's the motivator for this. So reviewer 3 might have a point about that, in which case you would want to look at the model that way instead, look at AIC and BIC, look at how the predictions are, look at all the conclusions and decide whether or not you want to keep that new model or keep the one that you have. But logit versus probit is not really a thing. I wouldn't talk about it at all, except for the fact that once you get into the world of structural equation models, so the idea of latent variables that are measured by multiple observed outcomes, in those models, there are different ways of estimating them in which you may have a choice of logit versus probit, or you may be stuck with probit instead of logit. So I'm setting the stage for that so that that metric becomes something you're at least familiar with or have heard before. But probits are z-scores. They are the z-score that corresponds to the area under the curve for the left up to that point of probability. That's what you can think of. Yes?
So then I have a question. So for example, you have a binary, like latent, you have a structure equation for like CFA, you have a binary response.
Mm-hmm.
Then it's kind of, well, the underlying curves look like that? Like you use a logit link function? Will the underlying line like that, looks like that, with the error of 3.29?
So this is pertaining to each individual outcome, not a latent factor.
Oh, okay. Mm-hmm.
So in a model in which, let's say that you have a checklist, like yes or no, I do these behaviors, and you want to use that to indicate some sort of latent variable for one standing on a trait, then the latent variable in those models is always assumed to be normally distributed. You'd have to develop a custom algorithm to get around that restriction. But the binary variables, you could say whatever you want about their underlying distributions because we have no data with which to even ascertain that. It literally doesn't matter. It's just a way to motivate the scale of the model in terms of what a unit is. And once you correct for the differences in scale, probit times 1.7 gets you to logit. then these give you basically the same predicted probabilities. Very, very small differences at certain points of this curve. I have, in the Excel sheet that goes with this example, I have a bunch of formulas worked out to demonstrate this across a logit solution and a probit solution, by the way. I did the last model both ways. Okay, so reviewer 3 may have, no Siri. That's where somehow she's defending reviewer 3. Can you believe this? And nowadays it's more like reviewer 2, because finding 3 reviewers for a paper is like a miracle. So reviewer 3 does not have a point. We would end up basically with the same conclusions, and it would be much harder to create predicted probabilities, and we wouldn't have odds ratios. But if they're recommending an asymmetric link, they might have a point. All right, ta-da! Any questions or comments on any of that, or things that you want to talk about again?
The decision to use the asymmetric, one of the asymmetric link function, can we base that on just the proportion of our outcome, like 0 ones, check the mean and see if we have more ones or more zeros? Can we base the decision on that?
My understanding is that the decision for which of the asymmetrics, like these two, is based on which is more frequent and how your model is phrased. So if you're predicting the one and the one is more frequent, you'd go log-log. Not all packages have both of these. Some packages only have one or the other, in which case you'd have to change what's 0 and what's a 1 to make it work. My understanding is that you can use AIC and BIC to judge whether or not these are better, or smaller is better for AIC and BIC metrics. Okay, anything else? Then homework 2 is your next task. I looked at it this morning, and a few of you have started, but most have not. So you should be able to do the first 2 sections, and then the third one is based on the interaction model that we're going to start with today. So do you have, let's see, I know we did a couple different days worth of looking at the empty model and the main effects model. Does anybody want to go over any of that again or have questions about it? Because we did those twice, maybe 3 times. All right, then let me pick up with the new one. Interactions. So I have stata and then I have R as usual to show you what it would look like both ways. So remember the story here, we are predicting the logit of whether or not someone has a shot at applying to graduate school based on their undergraduate GPA, whether their parents have a graduate degree, whether they went to private university, and now we are adding 2 interactions. So the interactions are between GPA and parent graduate degree, and GPA and private. What does this mean, by the way? GPA minus 3. Go ahead.
It's centered at 3.
Centered at 3. Why'd I do that?
GPA of 0 is not.
Yeah, GPA of 0 is not a thing. If you have a GPA of 0, you are not applying to graduate school. It's not going to go well. So I picked 3 because it was on a 4-point scale, and I'm sure that's not the mean, but it's at least a medium value that I can start from. These 2 interactions, what type of research question might motivate including them? What new additional information would I learn? I've got GPA by parent graduate degree and GPA by public versus private university.
Something like, does the effective GPA vary by whether or not the parent has a graduate degree or not?
Mhm.
And or like, does that effect vary by whether or not they attended private school?
Yep. Does the effective GPA differ for people who are legacies, can we call it that? Like whose parents went to graduate school? Is GPA more or less important in those kind of applicants? And likewise, is GPA more or less important if you go to private school or public school? What if I spin it the other way? If I start with this one, for instance. Does the effect of having a parent who went to graduate school depend on your GPA? Does that have a stronger effect in people who have high GPAs than low GPAs, for instance? Or does the differences between people who went to different types of schools, does those differences vary by GPA? That'd be another one. Yep. So adding two new terms at the same time, just for the sake of demonstration as to how you would do this. One of the articles on your reading list, by the way, has some very good arguments about why the translation into logits and probability can cause havoc in terms of interpreting interactions, because these are expressed in logits. The changes in probability don't necessarily obey the pattern that the logits are conveying. So I forget which article it was, but I know there's one of them. Let me pull that up real quick. Let me go to your syllabus and find it. It is, I think it's this one maybe, if memory serves. So there's also one about how to do power analysis for these sorts of designs too. And guess what? You need way more people to predict a binary outcome than you do a continuous one. Because a binary outcome is one step away from a constant. And it's very difficult to predict something with no variability. But we can compute the same types of model implied slopes as usual. So for instance, if I want to think about GPA as the target predictor and these other variables as moderators, then the GPA slope that is implied by the model would look like this. At a minimum, I need beta 1 because that is the effective GPA. Then I need how the GPA slope varies as a function of graduate degree and private schooling. So the logic of how to take apart an interaction term and figure out what it means is exactly the same. Once we have started predicting logits, your linear model skills all work exactly the same. The translation of those predictions into probability can be somewhat surprising, though. That's what the article is talking about. So we're in state of first here. We've got the command logit is what we're using. My two interactions are being defined on the fly like this with the hashtag /#, depending on how old you are. I am storing the results of this to do a likelihood ratio test against the previous models. And -2 log likelihood is what you need for your homework. So make sure that when you are entering it, that you're entering it into 2 digits after the decimal so that you can, do I have that in here? I don't think I printed it. That way you'll have enough digits to enter into the homework system. So this number right here is log likelihood. You'll have to multiply it by -2 to get the -2 log likelihood for the model. So this thing right here, first piece of output, do you remember what that is? What's LR stand for?
Likelihood ratio.
Yeah, likelihood ratio. So this is -2 times the difference in log likelihood for this model versus an empty model. In other words, this is not going to tell you if the interaction terms help. This is telling you about how a whole model works versus having nothing at all. What's the 5 in parentheses mean? Number of fixed slopes that I have, yep. So 1, 2, 3, 4, 5. So I have 3 variables, but I have 5 slopes, and that's why it's 5. Here's the p-value that goes with it. So we would conclude that yes, our model is significant. Yes, we're able to successfully predict this outcome to at least some extent. So this is the analog to what you used to have as an f-test for the significance of the model R-square in regression land. Then we can drill into the coefficients themselves. I think I put those, I put the questions in the R output, so we'll pause on that for just a minute. I'm asking for a likelihood ratio test as my next piece of output to compare against the previous model. So the model that we had before, which I called main, Oh, hang on. That is a copy-paste error. That's from my other class. Estimate store main is what that should be called. I'll fix that after class. I'm then recalling that in my new Stata model, storing interact there to do the 2. So this is how you can ask it to do the math for you, to take the difference in log likelihood between nested models, multiply by -2, and create a chi-square test statistic for that difference. So that's what this means right here. LR chi2 means chi-square. In parentheses, the number of slopes being tested. So the difference between these two models is my 2 new interaction terms. So my test statistic is 1.75. We treat that as a chi-square. P-value that goes with it is 0.42. So that means, on the whole, those 2 new slopes do not improve my prediction. And if I look at their individual p-values, I would come to the same conclusion. But you can think of it as this is the analog to how we would test for the change in R-square between nested models after adding things, like a stepwise or hierarchical regression. If I want to get predicted probabilities to make a picture or otherwise convey what my model is saying in margins, I can do that in Stata. These 3 numbers here mean start here from -1 in increments of 1 up to 1. So what this is doing is GPA of 2, 3, and 4, and then either possibility of 0s or 1s for my dummy code predictors. Predict XB, what's that mean? Feel free to read from the screen.
It's why having logits.
Yes, right here. I often have the answer on the screen because I'm shameless about encouraging audience participation. So XB is like what the model says it would be. So it's in the link transformed outcome, the linear predictor, as we say directly. If you want the probabilities, we leave it off. Then the default is probabilities. So there's 2 different sets of predictions, one in logits, one in probabilities. Then I have simple slopes. So when I type a variable name into these lincom statements, I am not referring to the variable, I'm referring to its slope. So this means beta 1. This interaction term is beta 4, which is shut off because I intend this prediction to be for someone without a degree. This one is also shut off because this is for someone who went to public school. So the math of what I'm doing is out here in the comments. In the last line, I would have the prediction of the slope of GPA, beta 1, for somebody whose parents went to graduate school and for somebody who went to private university. This model implies 4 different potential GPA slopes. Then last but not least, if I want the odds ratios to be printed for me, I add the magical OR at the end of the call, and that gets me a table called odds ratios. So in your homework, for every slope in a model, I've got in logits and odds ratios, and logits and odds ratios. Those are coming from 2 separate tables. And it's e to the slope coefficient in logits is where that number came from. But it gives you a standard error and confidence intervals around it too, which is helpful. And yes, like the p-value for GPA as a simple main effect is 0.104 here. It should match the p-value from logits exactly. It's the same information. So if you know what the p-value is for the slope in logits, you don't need to get it for odds ratios. It will hold. Okay. Any questions on Stata code? And output. All right. R code then. So in R, I'm using the function glm. This is base R. You don't have to install any packages for that. Formula, what goes there?
The outcome.
That's my outcome. Yep. Case sensitive, by the way. So can I tell you a story very quick of how I learned this the hard way? When I was teaching this class last year, and I was still teaching myself R in the process, I was preparing this very example, and I couldn't get R to do anything. And it was like 7 in the morning on a Saturday. I'd gotten up early to work on this because I was behind. I fought with R for like an hour, and it kept throwing these error messages, wouldn't do anything. And my husband wakes up, says hello, and I'm like, can you come help me? He hasn't even had coffee yet. He comes over to my computer. He looks at it and he goes, those are capital letters, and walks over to the coffee machine. Because in the data set, it was apply in capital letters. And I didn't realize that, and I kept typing apply in lowercase, and R's like, what? I don't know what you're even asking me. So yes, case sensitive. So I changed the data set so that it wasn't capital letters, and that way I don't have to get in trouble anymore. So apply to is what the name of the variable is. The 1, that's my fixed intercept. I type it to remind myself when I do ordering statements that it's there. Here's my 3 main effects. Here's my 2 interactions where the colon defines the interaction terms on the fly. By default, you don't get confidence intervals, so I added that. You also don't get BIC, so I added that. So here is my solution. Let's walk through it together. So, beta 0, this is my fixed intercept. It's a minus 0.66. Is that logits, odds, or probability? Logits. So if I have a negative logit, does that mean a probability above 0.5 or probability below 0.5? Below. Yeah, 0 is neutral in logits. So I have a logit of a probability of minus 0.65 as my reference point. Who is that the logit for, given the rest of my model? GPA 3, parents didn't go to grad school, went to public school. So the same principles in terms of linear models hold, you're just in logit land, which is a lot less fun than Disneyland or Dollyland or anywhere else we could go. GPA. Looks like my p-value is not significant. Can I say GPA doesn't matter? No, that's not the end of my sentence. Who is this the GPA slope for?
Reference person.
Yeah, people with whose parents didn't go to grad school, because that's where this variable is 0, and people who went to public university, because that's where this variable is 0. So this is what some would call a simple slope or a conditional slope. For that kind of person whose parents did not go to grad school and who went to public school, how do I talk about this? The slope estimate is 1.26. I'll start you off. For every
For every 1 unit increase in GPA,
Yep.
you get a 1.26 increase in the logits.
Exactly right. The logits of applying. Mm-hmm.
Applying.
Yep. For every unit increase in GPA, which is X, the logit of applying to graduate school increases by 1.26. Yes?
Why was that different for the intercept then? Like, why was the intercept about probability?
The intercept is in logits,
Okay.
but because the intercept is a predicted outcome, it's a predicted outcome for a particular person, but it is still a predicted outcome. I can take that into probability.
Okay.
Yep. I could take this logit coefficient. Do I still have Excel open? Sure I do. I can take that logit coefficient and I can turn it into odds. Oh. No, I do not want to accept your correction. I want to remove it myself. There. An odds of 0.5, and I can take that into, I'll go over the faster way, probability. 1 plus 1 to e to the minus logit, like that. 0.34 specifically. I can do that for the intercept because the intercept is a predicted outcome. I cannot do that for the rest of this because these are slopes.
Okay.
And I can take these and turn them into odds ratios. So like that logit, hang on, is, I do that one, equals e to the that thing. E to the logit, that's an odds ratio of 3.5. But then I got to stop. I can't do an odds ratio down into probability. So even if you don't know what the hell a logit is, as your GPA goes up, you are more likely to apply to grad school. That's what this means. You can think about a positive slope in the same way as x goes up, y goes up. It's only when you try to work with the coefficient itself that you have to remember that it's per unit GPA and the changes in logits specifically. But the direction is informative, always. Likewise, people whose parents went to graduate school are more likely to apply to graduate school or less? More. Yeah, you'd think their parents would have like informed them, but no, they're going to go anyway. Is that the end of my sentence? People whose parents went to graduate school are more likely to apply? Is that true for everybody? When GPA is 3. This is also a simple slope because of the interaction down here. Likewise, this one. People who went to private university are non-significantly more likely to apply, given the p-value. Let's do the interaction terms. Let's make the slope of GPA the predictor and then parent degree the moderator. The effective GPA is positive for people whose parents did not go to graduate school. What would I call it in people whose parents did go to graduate school? What does the interaction term do to it? Your choices are more positive, less positive, more negative, or less negative. Which one is this? This is a less positive. The slope is 1.25. It would become minus 0.83 smaller. So is the effective GPA stronger or weaker in kids whose parents went to graduate school? Weaker. Less anything is weaker. More anything is stronger. It's not significant, but I want you to know what to do with the coefficients. So I'd say non-significantly weaker effect of GPA in people whose parents went to grad school, and the result would be 1.25 minus 0.83 to get to what that slope would actually be. Same pattern if I go with private school. The slope is less positive in people who went to private universities. So then if I wanted to figure out what the resulting slope would be in the yes cases for this, that's where in R I would do this instead. Simple slopes. And yes, you get a chance to practice this in your homework as well. This is section 3. So these numbers are the multipliers of your fixed effects. You are creating linear combinations of your fixed effects. Why is the first number 0 in every single one of these? That's the intercept. Your intercept will never be used in computing the slope of something. The rule is, if you're computing the slope of something, the only terms that could be contributing have that slope as part of it. So the intercept doesn't have a slope in it. The column of 1s here, that is for the GPA slope because that's the thing we're trying to estimate. The next 2 are zeroed out everywhere because these are the main effects of the other variables that do not have the GPA slope. The last 2 are the interactions with GPA that can turn on or off depending on who the GPA slope is for. Okay, stop that. So the last one turns on if I'm talking about for someone who went to private. This first one turns on if I'm talking about someone whose parents had a degree, and if they had both, then they both turn on. So those are the 4 slopes implied by the model, and here's their output. So So it looks like actually GPA doesn't matter in any of these subgroups. But the power with which to test that depends on the size of the subgroup. So the p-value here is reflecting both the effect size and the sample size at the same time. All right, how are we doing? So if I ask for a likelihood ratio test to tell me if this model is better than the previous model, that's the next piece here. We're talking about significance testing. This is the ANOVA function that, as we discussed last time, has absolutely nothing to do with ANOVA. It is the analysis of deviance table, which I would prefer to be called ANODA instead of ANOVA, but no one asked me. The way this works is you point it towards the model object for the model that has fewer parameters, that is nested, that goes first. The model that has more goes second. And which kind of comparison you want, because there are multiple choices when it's used with GLM, I want an LRT. So then the results of this comparison tell you what the -2 log likelihood is for the first model, what it is for the second, how many terms it differs by, that's your degrees of freedom. This is the difference in -2 log likelihood between models, which is your test statistic that is treated as a chi-square, and here's the p-value that goes with it. So the results directly map onto what we found in Stata, of course. Then effect sizes, odds ratios. So I downloaded a separate package called DESC Tools to compute odds ratios this time. If it doesn't work for you, I just updated the online files that go with this example to have another way to compute odds ratios. So if this doesn't work, you can use that instead. So this is an odds ratio then. This is an odds, excuse me, since it's for the intercept. The rest of these are odds ratios, which are effect sizes for the rest of these. Odds ratios can never go negative. So if you see an odds ratio of 1, what does that mean about the slope? Say it again? That's what an odds would be. What about an odds ratio of 1? If I have a slope that has an odds ratio of 1, what kind of slope is it in logits?
Like it's 0.
It's 0, yeah. So a slope of 0 is an odds ratio of 1. Odds ratios from 1 to positive infinity go with positive slopes in logits. Odds ratios of 0 to 1 go with negative slopes. So odds ratios are always positive. I know. So here are the odds ratios for the model coefficients. I then did the same thing for the GLHT results. So this little table right here, where I estimated the 4 slopes for different kinds of people, I saved that as an object called int2 slopes. And then I asked for that object to have its slopes become odds ratios. So it's e to that object's coefficients. And here's that output. Last but not least, here's some predictions. So at the end of your homework, I asked for predicted outcomes for different kinds of people. This would be how you do it. The prediction function you can use for this. It allows you to make a list of all the ranges for your predictors that you want predictions for. Note there's 2 types. So type equals link corresponds to the idea of predict XB. That means in the linked metric, so we're in logits, and so that's what these would be. So these are all predicted logits for different kinds of people. If I want the probabilities instead, type equals response, and then it understands that I want probability based on the model that I fit. So these then are the logits back converted into probabilities. The very end of this, I pasted in a column. This is the prediction if I fit a probit model instead. So for instance, this kind of person here who has a GPA of 2 and 0s for the other predictors has a probability of applying to graduate school of 0.1283 from a logit model, a logistic regression. A probit model, a probit regression as it's called, is 0.1250. So they're off like that much. And if you look down the list, they're all off in like the third or fourth decimal place. So this is why I'm saying, does it matter? Probably not. And here's some pictures. So I made two different pictures to illustrate the interactions that we have here. These are slopes that correspond to the simple slopes for different kinds of people. So the x-axis is GPA in both of my pictures. The y-axis on the picture on the left here is the predicted logit of applying to graduate school. So if I have no parent graduate degree and I went to public school, that slope is 1.25 in logits. That's the red dashed line right here. The slope, if I went to private school instead, is the red solid line, so it's less steep. It's a slope coefficient of 0.57 in logits. The slope for, yes, my parents went to graduate school, but I went to public university, is the blue dashed line right here. And this one, I had to chuckle when I saw this. This is for somebody whose parents went to graduate school and they went to private school, and they are just done. They are not having it. So as GPA goes up, your logit actually goes down for that group of people, but it's not significant. So note that these are straight lines, okay? Coincidence or consequence? Consequence, because this model is linear with respect to predicting logits. It works the same way. A 1 unit change in x corresponds to the same change in logits always. It's a constant slope. But if I, instead of plotting predicted logits, so instead of plotting these values, I plot these probabilities instead, which is okay because I took a predicted outcome and I converted the outcome to probability, not the slope. Then I get this version on the right, which is the same information on a different y-axis. The y-axis is now the predicted logit of applying on a probability scale, which means I need to fix this thing here. Isn't it funny how you never find your typos until you're in front of people? No matter how hard I stare at this. I'll fix that after class too. Now look at these lines are kind of bendy. That's because we're approaching the bottom of the probability pool. So this red dotted line is starting to shut off as it gets down to 0. And the same thing would happen if I continue the prediction up. They would start to bend. So you can fit interaction terms that look like a clear pattern of interaction in logits, but when you plot them in probabilities, it may not look like the same pattern because of this compression of the slopes towards the ends. It can look like you've created an interaction where there isn't one, and vice versa when you translate from a logit to a probability. So you'll have to be very careful in describing the patterns to your reader. But predicted probabilities is what I would use to show what the model means. Predicted probabilities for different kinds of people. All right. So just to summarize, the model provides direct tests of the differences in logits. It indirectly provides tests of the differences in probability, but that's not what the coefficients are designed for. They're designed to predict logits. And as usual, words. So the way that I've written this, I talk about the logit and what happens to the logit, and then I give the standard error for that logit slope in parentheses along with the odds ratio. All right, questions? Feel like you can do this? Maybe? We'll find out, huh? That is always the question. It sounds reasonable, and you feel like you're following until you sit down and try to do it. Then you get to find out if you're really following. I've already moved homework 2, by the way, to be Wednesday the 1st. So you get an extra 2 days because I expected I would need today to get through everything, and I want to make sure you have at least a week between when I finish something and when you're responsible for it. So you can do all of homework 2 now. Hooray. All right. Do you want a preview of what we're doing next? Maybe not like a whole thing, but just a preview. So what if, instead of predicting, say, binary outcomes, I'm predicting categorical or outcomes like ordinal or nominal? Could I do that? Sure, I could. Like, what if I'm predicting someone's tendency to respond on a Likert scale from like 1 equals strongly disagree, 2 is disagree, 3 is neutral, 4 is agree, and 5 is strongly agree? Could I do that? Is that a continuous variable? Is that even a number? It's not, right? Like, we can call it 1 means this and 2 means this. That's not a number. That's not the same thing. So right off the bat, we know that the same issues in terms of going out of bounds, right? I can't have a model predict a response of 6 on a 5-point scale. I can't have a model predict a response of -1 on a 5-point scale. Likewise, if I wanted to predict what your major is going to be, right? And I might have something like arts and sciences versus engineering versus education versus something else. I might have 1 is arts and sciences, 2 is education, blah, blah, blah. Are those numbers? Not really. The numbers are labels, right? If that's the way they're stored, but they're not ordered in any way, shape, or form. I can't say that one major is like more than another. In the same way I can think of like more GPA or more of this. But what if I told you that you already know everything that you need to know to be able to predict those outcomes? Seriously. The way that it works is we're going to take each set of categories and we're going to divide them up in different ways into a series of binary, what I call submodels. And that's how these different models work. So let me show you one example. If I have an ordinal category, let me something a little, yeah, this one will do. If I have 4 options, one way that I can set up my model into a series of binary submodels is to divide them, but use all the categories in each binary one. Like 0 as one answer versus 1, 2, 3, 0, 1 versus 2, 3, 0, 1, 2 versus 3. This is what's known as an ordinal regression model. It is also known as a proportional odds model. It is also known as a graded response model, an IRT. But the idea is that we categorize the ordinal outcome into a series of binary models, and then we do the logistic regression on each of them at the same time. So that's what I mean when I say you already know how to do this. The only catch is that rather than saying it's the logit, you have to say the logit of what? The first model is the logit of answering something greater than 0. The second one is the logit of answering something greater than 1. And the last one is the logit of something greater than 2. That's how they work. From there, it's exactly the same. For other types of outcomes, for instance, nominal, where the categories are not ordered, it's dummy coding on the outcome side. You pick one category as your reference, and then you predict the logit of answering every other one relative to that as your binary submodels. That's called a nominal model. It's also called multinomial regression. It's a generalized logit link, people will call it that. But it's still a series of binary models. The other one that I know of that I'm not going to show you an example of because it's used much less commonly is what's known as a partial credit model, an IRT, or adjacent category logit. And then it divides it up into 0 versus 1, 1 versus 2, 2 versus 3. So yeah, all of categorical regression models works with this idea of a binary submodel as its core element. They just differ in what the 0 versus the 1 is in the binary submodels. And that's why the intro segment into this, the slide, I call it too logit to quit. Those of you who were alive in 1994 may remember this. This is a play on words of Too Legit to Quit, which is an MC Hammer song complete with a dance move, Too Legit to Quit. But here's the video for those of you who weren't alive or who want to revisit it. Once you understand how to predict a binary outcome, you know how to do categorical data analysis too. The hardest part about categorical data is figuring out what Y is at any given moment. Unfortunately, the software does not make this easier for you, but that's my job. So if we start with this just as an idea, binary submodels, dividing up categorical data into different binary submodels. So if I have 4 categories, I need 3 submodels. If I have 5 categories, I need 4. Same as making slopes for dummy codes. Same idea. All right. You feel like we can handle this? I think we can. But next time. How about that? Next time. In the meantime, I will say, let me know if you need anything as you're working on homework. Office hours are tomorrow afternoon. Vladimir has his on Friday as well, and then we'll hope to see everybody Thursday. So thanks for hanging in there. Happy Logit, everyone. Logits are amazing. Thank you, Zoomers.